Today we'll talk about generalization in learning using the method of version spaces. The issue of generalization in learning is closely connected to the issue of incremental concept learning. In both cases, there are a small set of examples arriving one at a time. In incremental concept learning, we made use of background knowledge. In generalization in learning, background knowledge may not be available. Similarly, in incremental concept learning, we control the order in which the examples arrived. But in generalization and learning, we may have no control over the ordering of the examples. Today, we'll start by defining version spaces. We'll talk about version spaces and as an abstract technique. Then we'll go into the algorithm for executing the technique of version spaces. We'll also, towards the end, talk about an alternative method for organizing the examples into a decision tree or an identification tree. This method is very similar to the method of incremental discrimination tree learning that we learned when we were talking about case-based reasoning.
Version spaces is a technique for learning concepts incrementally. This means that the technique is going to learn from a small set of examples that are going to arrive one example at a time. Now, we have come across a different notion of incremental concept learning earlier. In that technique, we started with the current concept definition. Then a new example would come about. In this case, it's a negative example, not an arch. And then a new concept characterization would be constructed by revising the concept characterization that we began with. The revision was such that the new concept characterization was a specialization of the old concept characterization such that the example got excluded. So negative examples led to specialization, positive examples led to generalization, and the ordering of these examples was important. We want the first example to be a positive example of the concept to be learned. We want the order to include both positive and negative examples. That technique was very useful when there was a teacher available who would give you these examples in the right order. Now, the order of examples was very important in that technique of incremental concept learning. We want a set of examples to include both positive and negative examples so that we can do generalization and specialization. And we want each example to differ from the previous concept characterization in only one important feature. In this case, the only important difference between the new example and the current concept characterization is that the two bricks touch each other. That the new example differs from the current concept characterization in exactly one feature is important because it focuses the attention of the learner. It tells the learner how to do the specialization or the generalization so as to include the difference or to exclude the difference. This technique is very useful if a teacher is available that can give the examples in a good order, in the right order, so that effective learning can occur. In that technique of incremental concept learning, we also consider the role of background knowledge. If the current concept characterization has brick or wedge at a node, and the learner has background knowledge which tells it that bricks and wedges are examples of blocks, then the learner can generalize from brick or wedge to a block here. But now we can ask two questions. What happens if these two factors, the presence of a teacher who gives examples in a particular order, and the availability of this background knowledge, tells the learner exactly how far to generalize? In general, in learning, deciding how much to generalize is a big problem. Learners tend to either overgeneralize, in which case they come to incorrect answers, or they tend to undergeneralize, in which case the answer might be correct but not very useful. If a child comes across a dog that is four-legged, furry, black, and called Buddy, and the child decides that a dog by definition is four-legged, furry, black, and called Buddy, then that is an example of undergeneralization. The conceptual characterization is correct, but not very useful because it will not transfer to any other dog. On the other hand, if the child decides that all four-legged, furry animals are dogs, then it's an example of overgeneralization because it could also include many cats. So the question now becomes, what would happen if the examples did not come in a good order? They came in an arbitrary order. And if this background knowledge was not available, in that case, the agent would have a hard time deciding how far to generalize. Version spaces is a technique that under certain conditions allows the agent to converge to the right generalization. So in the version spaces technique of learning concepts incrementally, We always have a specific model and a general model. As a new example comes along, we ask ourselves, is this a positive example of the concept to be learned or a negative example of the concept to be learned? If it's a positive example, then we generalize the specific model. If it's a negative example, we specialize the general model. Here is another set of visualizations to understand the specific and the general models. This is the specific model. This is the general model. The most specific model matches exactly one thing, the four-legged, furry, black animal called Buddy. The most general model matches everything, all animals. Here is a current specific model. And as more positive examples come, we're going to generalize this specific model. Here are some of the generalizations. Similarly, here is the current general model. And as negative examples come, we're going to specialize the general model, and here are some of the specializations. As we'll illustrate in a minute, or start with the most general model and try to specialize it. Some of these generalizations and specializations that we are creating will no longer match the current data. When that happens, we'll prune them out. As we prune on this side, as well on this side, the two pathways may merge depending on the ordering of the example. When they do merge, we have our solution, the right generalization of the concept for the given examples. So far, we have been talking about this in very abstract terms. Let's make this concrete with an illustration.
So, Ashok, I tend to think of the difference between the incremental concept learning we've talked about in the past and version spaces in terms of a bit of a visualization. We can imagine a spectrum that runs from a very specific model of a concept to a very general model of a concept. And we can imagine that this circle represents where our model currently is. If we receive a new positive example that's not currently subsumed by our concept, we're going to generalize it a bit to move it to the right. If we receive a negative example that is currently included in our concept, we're going to move it to the left and specialize. As more and more examples come in, we start to see that our concept keeps moving around, until eventually it lands somewhere that might represent a good model of that concept. So right here, we've landed on a model right here that's on the more specific end of the spectrum. So based on our examples, we decide that this is actually a pretty narrowly applicable concept. The general visual here, though, is that we had one concept that we're moving back and forth along the spectrum from specific to general based on our new examples. With version spaces, though, what we do is we start with both a specific model and a general model. So we take our dog example. If we've only ever encountered one dog, we might have a very specific model that says that any black, four-legged, furry animal named Buddy is a dog. We also might have an extremely general model that just says any non-human animal is a dog. So we have kind of the extremes of specificity and generality. Just like with incremental concept learning before, we then start to get examples. When we get a positive example, we're going to generalize our specific model. So let's say now the child witnesses a dog that's a little bit bigger and is blonde and has the name Scout. So now they're going to generalize their specific model a bit. So then maybe the child sees a cat and is told that the cat is not actually an example of a dog. So they specify their general model, maybe to leave out animals with pointy ears. Just like before, more and more examples keep coming in. But this time, with each new example, we're moving one concept or the other. Eventually what we see is that the model that was initially very specific and the model that was initially very general have converged. So not only has this helped us get to an understanding of the concept, but it's also figured out at what level of abstraction we ought to understand the concept.
Notice that David used the term model to refer to a concept. In fact, he used the term concept and models almost interchangeably. This is actually quite common for certain kinds of concepts. We have discussed earlier prototypical concepts when we were discussing classification. For prototypical concepts, concepts are like models. What is a model? A model is a representation of the world, such that there is a one-to-one correspondence between what is being represented in the world and the representation itself. As an example, in the world of those blocks that made arches, I can actually make an arch in the world, and then I can build a representation of that particular arch. That's a model of the world. So the concept of an arch and the model of an arch in this particular case can be used interchangeably. So let us suppose that I go to a number of restaurants and I have various kind of meals, and sometimes I get an allergic reaction. I do not understand why I'm getting this allergic reaction. Under what conditions do I get the allergic reactions? So I go to an AI agent and say, dear AI agent, tell me under what conditions do I get allergic reaction. And I give all the data shown in this table to the AI agent. Note that there are only 5 examples here. Like we mentioned, in knowledge-based AI, we want to do learning based on a small number of examples because that's how humans do learning. Note also that the first example is positive, and that they are both positive and negative examples. That is important so that we can construct both specializations and generalizations. How then may an AI agent decide the conditions under which I get allergic reaction? So these examples are coming one at a time, and let us see what happens when the first example comes. Here is the first example. The restaurant was Sam's, meal was breakfast, day was Friday, the cost was cheap. So from this one example, I can construct both a very specific model, which is exactly this example, Sam's, breakfast, Friday, cheap. You can't have anything more specific than this. And the AI agent can also construct the most general model, which of course is that it can be any restaurant, any meal, any day, and so on. You can't construct a more general model than this. So the most specialized model, based on this one example, says that I'm allergic when I go to Sam's and have breakfast on Fridays and the cost is cheap. And the most general model says I'm allergic to everything. No matter where I go, what meal I have, on what day, what the cost is, I feel allergic. Let us consider the processing as a second example comes along. And the red outline for this example means that it's a negative example. So now the AI agent will try to find a way of specializing the most general model and generalizing the most specialized model in order to account for this negative example. So given this negative example, we want to specialize the most general model so that this negative example is excluded. And yet, each of the specializations is a generalization of this most specific model because this was coming from a positive example. We do want to include this. Let's first specialize in a way so that each specialization is a generalization of this model. There are 4 ways of doing it because there are 4 slots here. The first slot here deals with the name of the restaurant, like Sam's or Kim's. One specialization of this most general concept is to put the name of an actual restaurant there. This is a generalization of this concept because this was referring to one specific meal at Sam's. This is referring to any meal at Sam's. In a similar way, I can specialize the filler at the second slot. Instead of having any meal, I can make it a breakfast meal. This is a specialization of this most general concept that is a generalization of this concept because this refers to breakfast at any place, this refers to breakfast at Sam's on Friday, and so on. Similarly for the third slot and the fourth slot in this most general concept. Now I must look at these specializations of the most general concept and ask which one of them should I prune so as to exclude the negative example. I notice that Sam's doesn't match Kim's, so this is already excluded insofar as this concept is concerned. Breakfast doesn't match lunch, so this example is already excluded insofar as this concept is concerned. However, this conceptual characterization admits this negative example. Therefore, I must prune it. So we prune away that particular conceptual characterization, and now we are left with 3 specializations of the most general model. Let us consider what happens when a third example comes along. And the green outline of this example shows that this is a positive example of the concept. Because this is the positive example of the concept, we must try to generalize the most specific model. So a generalization of the specific concept that includes this positive example is shown here. Here the meal was breakfast, here the meal was lunch, so we can generalize over any meal. Here the day was Saturday, here it was Friday, so we can generalize over any day. Of course, we could have also generalized to just Friday or Saturday, but for simplicity, we'll generalize over any day. Similarly for breakfast or lunch, generalize to any meal. But at this stage, there is another element of the processing. We must examine all the specializations of the most general concept and see whether any one of them needs to be pruned out. The pruning may need to be done in order to make sure that each specialization here is consistent with the positive examples that are coming in. So in this case, if we look at the first specialization here, which says I'm allergic to breakfast at any place on any day, this cannot be a generalization of this particular concept. Put another way, there is no way that this breakfast here can cover this positive example which deals with lunch. Put yet another way, the only way I can move from breakfast to any here would be if I generalize. But in this direction, I can only specialize. Therefore, this must be pruned out. As we prune this first concept out, we're left with only 2. Now let us consider the processing as a fourth example comes along. Again, the red outline shows that this is a negative example of the concept. Because this is a negative example, we must specialize the most general concept characterizations available at the moment. We can begin by checking whether we need to specialize this particular general concept. But wait, this general concept characterization already excludes this negative example. This says the allergic error happens when I go to Sam's, and this has Bob's in it, so this already excludes it. I don't have to specialize it anymore. Let us look at this general model. Does this need to be specialized in order to exclude it? Yes, because at the current stage, this includes this particular example. It has cheap hair, this is cheap, this is any hair, and this has particular elements for them. This means that this concept characterization must be specialized in a way that excludes this negative example, and yet the new specialization is consistent with the most specialized characterization at present. It is tempting to see the two pathways as converging here because this is identical to that. But we also have this branch hanging, and this branch says that I'm allergic to any meal at Sam's, not just a cheap meal. So we're not done yet. At this stage, there is one other element to consider. If there is a node that lies on a pathway starting from the most general concept characterization, that is subsumed by a node that comes from another pathway starting from the same general concept characterization, then I want to prune that particular node. The reason I want to prune this node is because this node is subsumed by this node. So if this node is true, I don't have to carry this around. If I'm allergic to any meal at Sam's, I don't have to specify that I'm allergic to a cheap meal at Sam's. Thus, I can prune this particular pathway, and I'm left with only this particular pathway. At this point in the processing, based on the examples that have been encountered so far, there are only two possibilities. I'm either allergic to everything at Sam's, or I'm allergic to every cheap meal at Sam's. I know you're wondering when this is going to end. We're almost done. Let's consider what happens when the fifth example comes. This is a negative example as indicated by the red outline. Because it's a negative example, we must specialize the most general characterization in such a way that this negative example is ruled out and the specialization is consistent with the most general version starting from the most specialized concept characterization. The only specialization of this general concept that both excludes this and is consistent with this node is Sam's cheap. It excludes this because it has cheap hair that will rule out the fact that this is expensive hair. Now the AI agent notices that these two particular concept characterizations are the same, and therefore convergence has occurred. Now we have the answer we wanted. I get allergies whenever I go to Sam's and have a cheap meal. What we have just done here is a very powerful idea in learning. Convergence is important because without convergence, a learning agent could zigzag forever in a large learning space. We want to ensure that the learning agent converges to some concept characterization and then remains stable. This method guarantees convergence as long as there is a sufficiently large number of examples. We needed 5 examples in this particular illustration for the convergence to occur. This convergence would have occurred irrespective of the order of the examples as long as the 5 examples were there. Note that we did not use background knowledge like we did in incremental concept learning. Note also that we did not assume that the teacher was providing the examples in the right order. This is the benefit of version-based learning. There is another feature to note. In incremental concept learning, we wanted each example to differ from the current concept characterization in exactly one feature so that the learning agent could focus its attention. However, in version spaces, you can notice that each successive example differs from the previous one in many features. Just look at the first 2 examples. They differ in many features, in the name of the restaurant, in the meal, in the cost. Here is the algorithm for the version space technique. We'll go through it very quickly because we have already illustrated it in detail. If the new example is positive, generalize all specific models to include it. Prune away the general models that cannot include the positive example. If the example is negative, specialize all the general models to include it. Prune away the specific models that cannot include the negative example. Prune away any model subsumed by the other models. Note that in the specific implementation of the version space technique that we just illustrated, there is a single pathway coming from the most specialized concept model. And therefore, there is no need to prune away specific models. In general, there could be multiple generalizations coming from the most specialized models, and this might be needed. Let us do some exercises together. This exercise actually is quite similar to the exercise we had done previously, except that we have added one more feature, vegan. Either the meal can be vegan or the meal is not vegan. Suppose this is the first example that comes along, and this is the positive example as indicated by the green outline. Write down the most specific and the most general models. What did you write down, David?
So this example is pretty similar to the first case we had in our previous example. So the most specific case is that I'm simply allergic to any breakfast at Kim's on a Friday that's cheap and isn't vegan. So this very specific example. And the most general model is that I'm just allergic to everything, no matter what meal it is, what day it is, how much it costs, whether it's vegan, or what restaurant I got it at.
Now suppose a second example comes along, and this example is also positive as indicated by the green outline. Based on the second example, would you specialize or would you generalize? What do you think, David, generalize or specialize?
So we said earlier that whenever we get a positive example, then we generalize our most specific model. So we need to generalize this model based on this new example. It's no longer sufficient to say that I'm just allergic to any breakfast at Kim's on a Friday that's cheap and not vegan. There's something else I'm allergic to.
That's right, David. So write down the generalization of this most specific model that is consistent with this positive example. What did you write down, David?
So in this case, the only difference between this and the previous positive example is that now it's lunch instead of breakfast. So the only thing we're going to generalize here is that now it can be any meal instead of just being breakfast. But we're still going to say that it has to be Kim's on Friday, it has to be cheap, and it can't be vegan.
And note that David could have put here breakfast or lunch, but for simplicity he has generalized it to any meal. Let's go a little bit further. Suppose a third example comes along, and this is the negative example indicated by the red outline here. What would you do this time, generalize or specialize? David, what do you think?
So this time we're going to specialize our most general model. It's obvious that I'm not allergic to absolutely everything everywhere because here's a particular instance where I wasn't allergic to what I ate. So we're going to specialize our most general model.
So like David said, given this negative example, we'll specialize this most general model, and we'll prune away those specializations that no longer match the data. Given this, how many specializations are left after the pruning? What do you think, David?
So I said that there'll be 3 potential general models left after specializing and pruning. Those 3 models are going to be that I could just be allergic to everything at Kim's, I could just always be allergic to breakfast, or I could just be allergic to eating on Friday. I would prune the ones based on cost and whether or not the meal is vegan, because although I've had bad reactions to cheap non-vegan meals in the past, here I didn't have a reaction to a cheap non-vegan meal. So it's not sufficient to say I'm allergic to everything non-vegan or I'm allergic to all cheap food.
We'd like you to complete this exercise. We've already done the first 3 examples. Having completed the exercise, decide which model did you converge on. Which one did you converge on, David?
So I converged onto this model over here that any cheap non-vegan food at Kim's is what's giving me my allergic reaction. We had left off by saying that potentially any food at Kim's or any breakfast or any cheap food gives me an allergic reaction. But the 4th visit rules out it being any meal at Kim's or any breakfast or any cheap food. It also rules out a couple other specializations like any breakfast at Kim's, any cheap food at Kim's, or any cheap breakfast. On a more specific model, we had left it off as any cheap non-vegan meal at Kim's on Friday, but visit 6 rules out the idea that it's just on Friday. It can also be on Saturday. So that leaves us with any cheap non-vegan meal at Kim's.
Note that in this exercise there were only 7 examples and only 5 features. So we could do it by hand. What would happen if the number of examples was much larger and the number of features were much larger? This algorithm would still work, but we'll need a lot more computing power. It is also possible that the algorithm may not be able to find the right concept to converge to because I might be allergic to multiple meals at multiple restaurants, such as breakfast at Kim's and lunch at Sam's. But even in that case, the benefit of this algorithm is it will show that convergence is not possible even after many, many examples. There is one other method we can use to process the kind of the data that we just saw. It's sometimes called decision tree learning. Recall that when we were discussing case-based reasoning, we talked about discrimination tree learning. There, we learned the discrimination tree incrementally. A case would come one at a time, and we would ask the question, what feature would discriminate between the existing cases and the new case? And then we'll pick a feature. Discrimination tree learning provides no guarantee of the optimality of this tree. That is to say, at retrieval time, when a new problem comes along, traversing this tree might take a long time because this tree is not the most optimal tree for storing these cases. We'll discuss an alternative method called decision tree learning, which will give us more optimal trees, however at a cost. The cost will be that all the examples will need to be given right at the beginning. Let us return to our restaurant example. We want to learn a decision tree that will classify these 5 examples so that as a new problem comes along, we can quickly find which is the closest example to that new problem. To do this, we need to pick one of the 4 features, restaurant, meal, day, or cost, that will separate these allergic reactions so that one category contains either only false instances or only true instances. As an example, supposing we think of restaurant as being the decisive feature. So we have picked restaurant as the decisive feature. Now there are 3 kinds of restaurants, Kim's, Bob's, and Sam's. Whenever it's Kim's restaurant or Bob's restaurant, there is no allergic reaction. Whenever it is Sam's restaurant, there can be allergic reaction shown in green here or no allergic reaction shown in red. So the good thing about this particular feature, restaurant, is that it has separated all the 5 examples into 2 classes, into the class Sam's and into the class not Sam's. The not Sam class consists of only negative reactions, which is good because we know that we have now been able to classify all of these 5 examples into 2 sets, one of which contains only negative examples. Now for these 3 examples, we must pick another feature that will separate them into positive and negative instances. In this case, we might consider cost to be that feature. When the cost is cheap, then we get positive examples. When the cost is expensive, then we get negative examples. This is the classification tree, and in fact, this is a very efficient classification tree. When a new problem comes along, for example, visit 6, Sam's, lunch, Friday, cost is expensive, and we want to decide what the allergic reaction might be, we simply have to traverse through this tree to find out the closest neighbor of that particular new example. This is called a decision tree, and this technique that we just discussed is called decision tree learning. This method of inductive decision tree learning worked much more efficiently and apparently more easily than earlier methods we had discussed. But the trade-off is that we needed to know all the 5 examples right in the beginning. Of course, this technique simply appears to be efficient and easy, and that is because we had only 5 examples and only 4 features that were describing all 5 examples. If the number of examples was very large, or the number of features describing each examples were very large, then it's very hard to decide what exactly should be the feature that we should use to discriminate on. Let us look at another example of decision tree learning. Here is a data set of people who go to the beach, and some of them get sunburned and others don't. In this data set, there are 9 examples, and each example is characterized by 4 features: hair, height, age, and lotion. Once again, how can we construct an optimal decision tree that will classify all of those examples? One possibility is to discriminate first on hair color. Hair color classifies all of these 9 examples into 3 categories: brown, red, and blonde. The interesting thing about the choice of hair color is that in case of brown, all the sunburn cases are negative. People with brown hair apparently don't get sunburn. In case of all the red-haired people, there is sunburn. So hair color is a good choice for picking as the feature to discriminate on, because it classifies things in such a way that some of the categories have only negative instances and no positive instances, and some of the categories have only positive instances and no negative instances. Of course, that still leaves blonde-haired people. In this case, there are both some positive instances and some negative instances, and therefore we need another feature to discriminate between the positive and the negative instances. Here, lotion might be the second feature that we pick. Lotion now classifies the remaining examples into 2 categories. Some people used lotion, other people did not. Those who used lotion did not get sunburn. Those who did not use lotion did get sunburn. Once again, these are all negative instances. These are consisting of only positive instances. Thus, in this decision tree, simply by using 2 features, we were able to classify all of these 9 examples. This is a different decision tree for the same data set. But because we used a different order, therefore, now we have to do more work. This decision tree is less optimal than the previous one. We could have chosen a different set of features in a different order. Perhaps we could first discriminate on height, and then on hair color and age. In this case, we get a much bushier tree. Clearly, this tree is less optimal than this one. Note the trade-off between decision tree learning and discrimination tree learning that we covered in case-based reasoning. Decision tree learning leads to more optimal classification trees. but there is a requirement. You need all the examples right up front. Discrimination tree learning may lead to suboptimal trees, but you can learn incrementally.
So how would version spaces be useful to answer Raven's progressive matrices? Like with incremental concept learning, think first about what concept you're trying to learn. Are you learning transformations? Are you learning types of problems? What are the increments? Are they individual problems? Are they individual figures? Are they individual transformations in a problem? Second, what are you converging onto? For example, you could use version spaces within one problem and converge down onto a correct answer. Or you could use it for learning how to solve problems in general and converge onto an optimal algorithm. Or you could use it for learning an ontology of problems and converge onto a single type of problem you expect to see in the future. So what are you converging onto if you use version spaces for Raven's progressive matrices? So today we've talked about version spaces. Version spaces are an algorithm for converging onto an understanding of a concept, even in the absence of prior background knowledge or an intelligent teacher. We covered the algorithm for version spaces where we iteratively refine a general and specific model of a concept until they converge down onto one another. We then talked about using version spaces to address more complex problems. We've also connected version spaces to older concepts like incremental concept learning. Finally, we talked about the limitations of version spaces, such as what to do if there's no single correct concept, or what to do in the absence of either positive or negative examples. To address these, we also covered identification trees, which are a different way of approaching the same kind of data that version spaces operate on. We'll touch on version spaces and incremental concept learning again when we talk about mistake-based learning.
Cognitive agents, too, face the issue of how far to generalize. We can undergeneralize, in which case what we learn is not very useful. We can overgeneralize, in which case what we learn need not be correct. For example, imagine that I was a Martian who came to your Earth. I saw the first human being, and I might undergeneralize and say, this specific person has 2 arms. That is not very useful because that is not applicable to any other human being. Or I might overgeneralize and say, everyone on this Earth has 2 arms. That need not be correct. Version spaces is a technique that allows convergence to the right level of abstraction. This is also connected to the notion of cognitive flexibility. Cognitive flexibility occurs when the agent has multiple characterizations or multiple perspectives on the same thing. As we saw in version spaces, the agent has several possible definitions for a concept that converge over time. An alternative view is to come up with one generalization and try it out in the world. See how well it works. If it leads to a mistake or a failure, then one can learn by correcting that mistake. We'll return to this topic a little bit later in the class.
Please write down what you learned in this lesson.
Great, thank you so much for your feedback.